Okay, so to continue our discussion, moving on, we'll be talking about conditional probability, but we'll kind of tie in together the stuff that we just saw with Venns, but more particularly with two-way tables, right? So I'm going to go back to the idea of that problem with students who have pierced ears or not. Okay, so let's talk about if we know that a randomly selected student has pierced ears. What is the probability that the student is male? Okay, so there's a total of 103 with pierced ears, right? So you know that you're talking about those 103 because they say, what is, if we know that a randomly selected student has pierced ears, that means we already know they have pierced ears, so it has to be out of that 103. There's a 19 of those among the 103 that have pierced ears, okay? So, in other words, I'm asking you for what is the probability that the student's going to be male, given that you already know the students have pierced ears. So that's 19 males out of the 103 that you know already have pierced ears. So that's about 18.4%, right? So when we did that, when we were looking at that, we were restricting our attention only to that column, that 103, okay? What if I switch the question slightly, right? And now I said, if we know that a randomly selected student is male, what is the probability that the student has pierced ears? So now we're saying, what if we know they are males? That means we're looking at just the male row here, okay? So we know we're restricted to only taking a look at 90 students, and in that group of 90 male students, how many of them have pierced ears? Well, that would be 19, right? So about 21.1%. So this time we only focused on the group for males. So where it seems like I was asking you the same question, they are really quite different. So a probability like the probability that a randomly selected student is male given that the student has pierced ears, that's known as a conditional probability. The name comes from the fact that we are trying to find the probability that one event will happen under the condition that some other event is already known to have occurred. So we already knew we were just talking about students with pierced ears, or we were just talking about students who were male. We'll often use a phrase given that to signal the condition that we're focusing on. So we have to focus in on one condition. Males focus in on pierced ears. Okay, so the probability that one event happens, given that the other event is already known, is known to have happened, is called the conditional probability. Suppose we know that event A has happened, then the event that B happens, given that A happens, is denoted by the following, where that is read as given that or under the condition that. Okay, so kind of flip-flopping between examples here. So back to the New York Times USA Today problem. Okay, so now what if I asked you for the probability that a randomly selected resident who reads USA Today will also read the New York Times. So now you are talking about restricting your focus only to residents who read the USA Today. You want to know of them how many of them also read the New York Times. Okay, so you're looking at the probability of B given that A happened. Okay, so in other words, the probability that they read the New York Times given that you already know that they read USA Today, which means that total of A would be the 0.4 that's going to go in the denominator. The probability that they read both we know is 0.05. So the probability that they would read New York Times, 0.05, given that they read, they already read USA Today, which would be over 0.5, would be about 0.125. So there is a 12.5% chance that a randomly selected resident who reads USA Today also reads the New York Times. We are going to do this in class on Friday. Okay, so let's suppose now that A and B are two events resulting from the same chance process. Then the probability of A or B. Okay, hang on. Let me just write some stuff down for you. Okay, the probability. We know that the probability of A or B is the probability of A union B, which is going to be found by taking the probability of A plus the probability of B, and we're going to subtract out that overlap, okay, the intersection of A and B, okay? But the problem is, how do we always find this, right? So it is very easy to find when you have a Venn diagram or when you possibly have a two-way table, but you may not always have these things. So how do you find it, right? Well, the word and often in probability kind of implies multiplication, okay? So you know that we're going to be multiplying somewhere, but what are we multiplying would be the question. Okay, so what I'm describing here is the general multiplication rule. So when the probability that events A and B both occur can be found using your general multiplication rule. So this is like something more like you don't have a Venn diagram or you don't have the information to make a Venn diagram or a two-way table. Then you would have to rely on multiplication. So how you would find the probability of A intersection B or end B would be to take the probability of A, or the first event, and multiply it by the probability that B will occur given that A already occurred, okay? Let's take a look at an example so we can kind of see how this works. Okay, so the Pew Internet and American Life project finds that 93% of teenagers ages 12 to 17 use the internet, and that 55% of online teens have posted a profile on social networking sites. Find the probability that a randomly selected teen uses the internet and has also posted a profile. So they are doing both things. So we know that in a Venn diagram, this would be the overlap. So we already know that the probability that they use the internet is 93%. Okay, and the probability that they have a profile, given that they use the internet, because it says of online teens, is 0.55. So the probability that they have that they use online and they also have a profile will be the probability that they use online times the conditional probability that they have a profile given they use online. So the 0.93 times the 0.55 would be 0.5115, which implies 15% of teens are online, and they also have posted a profile. That is it for video 2.